Hello, so this is a next video in the series on eigenfunctions of the Fourier transform. So this is a part of a playlist. You can go and watch what I was saying in the previous video. Basically, I started with some subspace V, which are polynomials times the Gaussian, or just that. And I showed that this right here was dense in L2. And V was made of V0, V1, V2. This right here is one-dimensional, two-dimensional, three-dimensional. And this right here is just span of a Gaussian, multiples. I mean, in general, the Vn is Cnx. So polynomials of degree at most n times the Gaussian. And this right here, we're all invariant subspaces. And basically, starting with here, I start with an eigenfunction. And then every time I increase the subspace by dimension 1, I'm adding new eigenfunctions. So in principle, I do have an eigenfunction decomposition because I can find eigenfunctions in here. The space, the union of all these is dense in L2. So I get a complete orthonormal basis, basically, and of eigenfunctions for the Fourier transform. However, it doesn't really tell you what the eigenfunction basis is, so we're going to explore that a little bit more. So the proof, so often what happens is how people approach it is they use this operator here, x squared plus d squared. It's related to what they call the quantum harmonic oscillator. I'm not going to really go into that at all. I'll talk about a little bit more how you can find some resources on that. However, I do want to talk about some things related to it and why it's kind of a natural thing to study. So, theorem, if you have f, it's an eigenfunction of the Fourier transform. Now, this function is going to be a Schwartz function. Then, so is this thing. If I take x plus id, applied to f, I also get another eigenfunction. So let's see why. If you do f, x plus id, well, what is that? So fx, and then fi, fd. Now, the x, when it moves over, it turns into a d. The d, when it moves over, turns into negative x. That here. Now, I want to write it like kind of like this in some way. So let me factor out the negative I. So negative I times x and f. If I factor out a negative I here, so I have negative I, and then I have to multiply by I, because the I squared is -1. So I get x plus id with a negative I here times f. And you see it's the same operator here, except the negative I. So these things don't commute, but they commute kind of up to a factor. There's a factor that comes out. And that's the key thing that's going to actually make this work. If I have f that's an eigenfunction, this thing is going to be an eigenfunction with a different eigenvalue. So let's see why. F hat is lambda y, f. So this is an eigenfunction of the Fourier transform. Now we're going to calculate the eigenfunction of this. The Fourier transform of this, see if it's an eigenfunction. So Fourier transform, x plus id. Now we know this identity. You can interchange them. The f comes over here, we get this, except that you get a negative I. Now we can do this, we get lambda f. So we get minus I lambda x plus id times f. These things in here are the same thing. So this thing is an eigenfunction of Fourier transform with eigenvalue this, or it's 0. So either that or this thing is 0. It's either an eigenfunction or it's 0. The rest of the proof is to show that it's not 0, because f is an eigenfunction. That means it satisfies this and it's non-zero. So I just need to show that this thing is non-zero. So why is that true? Well, let's see what happens if it is 0. So if this thing is 0, then what does that mean? Well, x means multiply by x. id, so d is I over 2 pi derivative. So if I multiply by I, it's negative 1 over 2 pi f prime. And this is equal to 0. So this is a differential equation. So being in the kernel of this operator, so this thing times f is 0, tells me that f satisfies a differential equation. So what is that differential equation? Let's try to solve it. So let's isolate f prime. So we're going to move this thing over and multiply by 2 pi. So the derivative is 2 pi xf. Now what we can do is we can solve it. So f has to be a constant times e to the integral of this thing. That's going to be c e to the pi x squared. Now, because the function is a Schwartz function, or even if I assumed it was an L2, this is a Gaussian that's exploding, unless c is 0. So the only way that this thing can be a Schwartz function decaying at infinity is that c is 0, which just tells me that f is 0. And f being 0 contradicts the fact that I assumed that it was a 0 because I assumed that it was an eigenfunction. So it tells me that this thing is non-zero whenever f is non-zero. And it's an eigenfunction. Okay, so that completes that idea. So this is what they call the raising operator, and I'll talk about that a little bit. So basically, the idea is that if I think about this operator, x squared plus d squared, what you can show is that its eigenvalues using raising operators and what's called the lowering operator with the minus ID is that they're one-dimensional subspaces, and they have like this ladder right here. So this is a one-dimensional. This is the lowest eigenvalue, and this is the next lowest, and then et cetera, et cetera. The raising operators will move x squared plus ID up here. They'll move an eigenfunction down here with a certain eigenvalue up, and then you apply it again, and it goes up and up and up. The lowering operator does it in the opposite direction. Now, these spaces right here turn out, as far as the Fourier transform is concerned, to be on the unit circle. So this one right here, the lowest one, turns out to just be the Gaussian. That's x minus ID. F is 0. So let's see why that's. You can show that x plus ID. Oh, this is actually what we showed, is that it's x plus ID. F times minus I. But if you do the Fourier transform with the negative sign, let's actually go back up with the negative sign. If you do the negative sign here, negative, negative, this is a plus. Then what happens? You get a plus here. When you pull it out, you're not pulling out negative I, you're pulling out I, which means you have a negative here. So you see f x minus ID has an I here with the same operator. So if you had a minus sign here, minus sign, then you're going to have an I here. So what it means is that if you have a Fourier transform, you do the Fourier transform with a function that's an eigenfunction, then if you do x minus ID of f, then it's going to have eigenvalue negative, just positive I lambda. So it's just rotating around the unit circle. So if I started here, the raising operator, this is the Gaussian. I said this was a Gaussian. The reason why it's a Gaussian is if I do x minus ID, f times 0 is 0. If I do the Fourier transform of both sides, sorry, if I write out what this is x plus 1 over 2 pi f prime is equal to 0. And that's f prime is minus 2 pi xf, which tells me if you just solve it using the exact same method we used before, we see that f is a multiple of the Gaussian. So the Gaussian is the kernel of this operator. And it turns out, if f satisfies this, kernel thing here, and you do the Fourier transform of it, you do the Fourier transform of this f at 0. If I do x minus ID here, when I interchange these two, I'm going to get an I, x minus ID, Fourier transform f. Now this thing was 0, so I just get 0. So because these things, the x minus ID, the lowering operator, commutes with the Fourier transform up to a face, it means that it's going to preserve the kernel of x minus ID. And because it preserves the kernel of x minus ID, it means that this function, which is a Gaussian, when I do the Fourier transform of the Gaussian, I get a multiple of the Gaussian, because the multiples of the Gaussian are the only things in the kernel. And because the Fourier transform preserves the L2 norm, you can show that the C here has to have +1, I mean, you basically can just calculate the Fourier transform at the single value 0. And you see that equals 1, which tells you that the constant here has to be 1. Anyway, I don't want to get too much into some of the details. I'm going off into a tangent. The idea is that this x squared plus x squared plus d squared has this ladder of eigenvalues with different eigenspaces. And the raising operator, x plus id, will move you up, x minus id will move you down. And the idea is that these are all one-dimensional subspaces. As far as the Fourier transform is concerned, you basically have large repetition of eigenvalues. If you start here, this is the eigenvalue with the Gaussian, this lowest one. And when you apply x plus id, that rotates you around and just keeps repeating over and over and over again. So what you do is you end up, if you do this approach here with this operator, and you find all its eigenspaces and all the eigenfunctions, it actually separates out the fact, it's kind of like a cover, if you know what that means. Basically, you're unwinding the fact that the Fourier transform is winding around and around and around, and then you're kind of undoing all the multiplicity. Anyway, so that's kind of the story, the big story. If you want to see more about it, which I'll go down here and I'll mention it briefly. There's this nice video series by MIT OpenCourseWare, the Quantum Mechanics 1 course, where they talk about the harmonic oscillator with operator methods. They have the lecture 8 talks about the harmonic oscillator using differential equations, but lecture 9 is kind of more in spirit with what we're talking about in terms of raising low end operators and such. It's a very interesting story, so I highly recommend it. In fact, the whole series. Anyway, let's do this theorem here, which is another thing that's related to this whole picture that we had here. If you have f, which is an eigenfunction of n, and also of this operator here, then it's an eigenfunction of the Fourier transform. So before we prove this, let's make two remarks. The first remark is, what does it mean to be an eigenfunction of this thing? Well, it's x squared plus d squared f is alpha f. If you translate this in terms of what this means, x squared f is x squared f. D squared f is, well, d is I over 2 pi times the derivative. So if I do it twice, I get negative 1 over 4 pi squared. Second derivative, that's this, equals alpha f. So basically, it's a second order differential equation. Being an eigenfunction of this is a second order differential equation. Now, as a remark, the Fourier transform will commute with x squared plus d squared. You can do them in any order. Well, why is that true? We have f, x squared, d squared. You do that here. Every time you pull the x over, it turns into a d. So I pull the x over, it turns into a d. I pull the d over, it turns into a negative x. But when I do it twice, the x over comes over again, get d squared. D comes over again, I get negative x times negative x, that's x squared. And then I group, and then I see these things are the same thing. So these operators commute. So what it means is that the eigenfunctions of this will be preserved by the Fourier transform. And so what I want to say is this, what this theorem says is that if I know that it's an eigenfunction of n and an eigenfunction of this, then I know it's an eigenfunction of this. So let's go down and see that. Suppose that this thing is true. So eigenfunction of x squared plus d squared. We just already said that this thing is the same thing as being a solution to this differential equation here. I just moved the alpha f over and I wrote it in as a homogeneous differential equation. In general, a second order differential equation has two initial conditions, which is the value at some point and the derivative at that point. We're just going to choose the initial point to be 0. And we'll see why in a second. If you know the initial conditions, two initial conditions, which are vectors in R2 or C2, I guess, two-dimensional space, then it determines it uniquely the solution. And in fact, if you have two initial conditions, you have one initial condition, f0 and f0 prime, and you have another initial condition, which is g0, g0 prime. If these vectors in R2 are linearly independent, then the functions are linearly independent. That's the key thing, is that, for instance, if this vector is the certain multiple of this vector, then the functions are actually the same multiples of each other. That's the key thing about initial conditions. The key thing about initial conditions that tell you about the uniqueness of the function. That's the key role that they play in terms of uniqueness. Anyway, so let's see. We know that this is true. So if f satisfies this initial condition, that's the same thing as having this eigenvalue for this operator, then the Fourier transform will also satisfy the same equation, which is the same thing as satisfying the same ODE. And the question is, so they satisfy the same ODE. That doesn't mean they're multiples of each other, because you need initial conditions to match up in some way to be multiples of each other. Turns out that's the role then, and we'll tell you that these are multiples of each other in a certain sense. So suppose NF is F, so it's an eigenvalue 1 for N. Well, that just means that f of x is f of negative x. That's what NF is, and that's just F. So that's the same. This right here is equivalent to F being even. And that turns out to be equivalent to F hat being even. Now, F hat being even, if you look at the Gaussian, for instance, any even function has a derivative 0 at the origin. So F and F hat are even tells you that their derivative at 0 are both 0. Also, if you have eigenvalue negative 1 for N, that means f of negative x is negative f of x. That means f is odd. That's the same thing as f being odd. And f being odd is equivalent to f hat being odd. Now, odd functions always are 0 at the origin. So odd function tells you it's 0. The Fourier transform is odd, tells you that it's 0 at the origin. In either case, one of these initial conditions are 0. One of these are 0. So the picture looks like my initial condition is here and here. They're both lying on the same line. Or one is 0 and then the other is 0. They all lie on the same line as far as linear independence is concerned. So what we see is that f and f hat, based off being an eigenfunction of n, they have the same initial conditions. I mean, they have initial conditions that are linearly dependent. So by the uniqueness of ODEs, f and f hat are linearly dependent. Now, what does that mean? Well, if f is not 0, because it's an eigenfunction, then f hat is going to be a multiple of f, like this. And, if f was 0, f hat is then 0, so this still holds. The point is that we had an eigenfunction for x squared, d squared, and for n, both of them, and then it tells you it's an eigenfunction of the Fourier transform. Now, the key thing about that story, so anyway, let's continue. So a way, based off what we said, is a way to obtain an eigenbasis for the Fourier transform is to find an eigenbasis for this, consisting of even and odd functions. That's just Fourier transforms of eigenfunctions of n. And it turns out, yeah, so this is the thing that I jumped down to with this discussion here. The thing that we talked about just a second ago, which was that this picture here. It turns out this picture has those properties, that this function down here, the Gaussian, is even. Then when you go up and you use a raising operator, it gets odd, and then it becomes even again, it becomes odd, it becomes even again. And the key thing is that this this decomposition that you get right here is exactly just the eigenfunctions and eigenvalues of x squared plus d squared is all you need. It turns out that n isn't actually even relevant. Because eigenfunctions of x squared plus d squared turn out to be even or odd. And why is that true? I mean, well, first of all, we showed earlier that n and x anti-commute, which means that if you do n x squared, if you pull x over twice, you get a negative x twice, which you get x squared n. And you can do the same thing. You can show that nd is negative dn. So if you do n d squared, it's d squared n. So n commutes with x squared and with d squared. So n commutes with this. So it turns out that this thing has all of the eigenfunctions that you need, basically. If you find the eigenfunctions of this, you can assume that they're even and odd. However, that doesn't actually tell you why all of the eigenfunctions here are even and odd. I mean, these commuting just tells you that this thing and this thing commuting tells you can find eigenfunctions that are even and odd. Eigenfunctions of this that are even and odd. However, it doesn't tell you that they have to be even and odd. And I mean, if you just look at this differential equation here, you could just easily imagine giving initial conditions that make the function not even and odd. You just make these both equal to 1. This function won't be even and or odd. However, you could then think about it. Just what that's saying is that yeah, it's an interesting thing to think about. It might be a thing related to the being in L2, where if you give it the wrong initial conditions, it might no longer be in L2. That might be the reason why. There might be other reasons. I think my gut feeling, that's probably the reason why. However, I'm not sure. So that's something to look into a little bit more. The rest of this slide is just giving some examples. So we have this Gaussian here. If I do the raising operator to the Gaussian, what you get is, I'm not going to go through all the calculations. You basically take this thing and you get a higher degree polynomial times the Gaussian. Degree, it always increases it by 1. And what you see here is this is that example that we had earlier on the first slide, which is all the way back here, which was all the way down here on the bottom, which is the Fourier transform of x e to the pi x squared has negative I. And that's what I have here. This thing, if I do the raising operator on it, this thing has eigenvalue 1. And when I do raising operator, it makes the eigenvalue negative I times lambda. So it's going to be now negative I. And that's what I showed. This thing has eigenvalue negative I. If you do it again, it's going to have negative I squared, which is negative 1. So this function right here has eigenvalue negative 1. And then you can just continue if you like. This thing is going to have negative I cubed, and et cetera, et cetera. And you see that every time it's increasing polynomial degree. One thing you can see that if you do p of x e to the minus pi x squared, and you do the raising operator x plus id to it, well, what is that? That's x minus 1 over 2 pi derivative p of x e to the minus pi x squared. So what happens when you do this? So this is going to be x p of x. Let's factor out the Gaussian. If I do the derivative minus, if I do the derivative on p, that's going to be p prime over 2 pi. Not too interesting. Derivative of this Gaussian. If I do the derivative of the Gaussian, that's minus 2 pi x, the Gaussian. If I divide by negative 2 pi, that's x times the Gaussian. So that's plus x p of x. So that's 2x p of x minus p prime over 2 pi times the Gaussian. So you see here, the p of x turned into 2x p of x minus the derivative. So you see here is that it's increasing the dimension by 1. And that's actually why you can see that this thing is the raising operator, because it took the p and it increased the dimension. However, if you had x minus id, this is where you can see that it's the lowering operator, because instead of having x Gaussian, you can get negative x. So everything is the same here, except for these signs here are different. So x p of x plus p prime over 2 pi minus x p of x. And now, because you have the minus I here, the minus I turns into just a normal derivative over 2 pi. And then the normal derivative with this negative exponential term up here makes multiplying by x cancel. So these cancel here, and then you decrease the degree of the polynomial. So that's why it's a lowering operator. So that's kind of a neat thing to look at. So we've already explored, so we haven't said exactly what's up. So basically we said x plus id, if you do the Gaussian here, these right here are going to generate, you can check with this right here. What you need is that this thing is always even or odd. So the key thing is that this thing is even. If you apply this thing every time, it's going to interchange even and odd. So why is that true? This thing is even, right? So how does this thing commute with this? Well, it turns out it commutes with a negative sign. Why does it commute with a negative sign? Well, the reason is it commutes with the Fourier transform with the negative I. So when you interchange these, let's do it with f squared, which is just n. Every time you pull an f over, it turns into a negative I. So you get negative I squared, f squared x plus id. And then that's just negative n x plus id. So you get a negative sign here. And what it means is that if you start with an eigenfunction of this thing, x plus id, that's the Gaussian. Or where is it? The Gaussian. Pi. You start with an eigenfunction of sorry. You start with the eigenfunction for n, which is even or odd. Every time you apply x plus id, it's going to change the sign of the eigenfunction for n. So it's going to take an even function. Every time you do it, you're going to get an odd function, even function, odd function, even function. And then that is going to then generate that's just the raising and lowering operator idea that we had up here, which is that you need the function to be an eigenfunction of x squared, d squared, and of n. And it turns out that if you go through this whole method, that is what you'll get. So basically, we showed that x plus id times the Gaussian, these are going to be eigenfunctions. And we found out what the eigenvalues were. It's negative I to the n. And we showed that they alternate even and odd. And there are different dimensions every time. So basically, these right here will span that space V. And then we have the eigenvalues. And so this right here becomes our explicit example of orthonormal bases, except we just need to normalize them. So this is an orthogonal set that once you normalize the vectors in L2, you get an orthonormal basis. And in the next video, we'll talk about the how to normalize them in a certain way and a different perspective on the orthogonality.